So here we have a couple of problems relating to simple harmonic motion. So the first problem says the graph below shows the motion of an oscillator undergoing simple harmonic motion. What is the equation that describes this motion? And also mark on the graph when the oscillator is at equilibrium and also when the oscillator has zero velocity. So as a reminder, the form for simple harmonic motion, or one possible form, is x as a function of t, so position as a function of time, is a times cosine omega t. Okay? Where a is an amplitude and omega is the angular frequency. So I think I'd like to come back to those, and maybe first let's plot or label on the graph where the oscillator is at equilibrium and where it has zero velocity. So I'm going to circle those, and in red I will circle places where it's at equilibrium, and in blue I will circle positions where it has zero velocity. So equilibrium is the central position. It's the position about which the oscillator is oscillating, right? So the average x position here is 0, right? This is oscillating around x equals 0. So all of these zero crossings here are positions, or times rather, where the oscillator is at 0. The oscillator has zero velocity whenever it's at a maximum or a minimum. Right? In fact, you can relate this to velocity is the slope of a position versus time graph. Right? So the slope is 0 at each of these peaks. Okay, so now we can identify the bits that we need here. T is a variable, so we don't need any value for t, but we do need to find the amplitude and the angular frequency. Well, amplitude is simply the maximum displacement from equilibrium, right? So it's how high or how low this graph goes. So I could label maybe this distance here, that is an amplitude. Or I could label maybe this distance here, that is also the amplitude. And if we look, this goes all the way up to maybe 2.5 centimeters, and all the way down to 2.5 centimeters below this axis. So A is 2.5 centimeters. Alright, and we'll mark that just so that we can see it later. Alright, so that was pretty straightforward. We could find this directly off of the graph. But the angular frequency is not as straightforward. Alright, because omega is not something I can label on this graph. Alright, but if you remember, recall that omega is related to the period in this way. Right, so t is the period, and that is the peak-to-peak or valley-to-valley distance on this graph. Alright, so if I label from a valley to a valley, that is one period, t, or I could label a peak to a peak, that's a period. But really, it's the amount of time that it takes for this cycle to repeat itself. So I could pick any 2 points that are the same. So here we have the graph is going down past 0, and here the graph is going down past 0. So I could label that distance as well. That's also a period, right? And that's okay because all of these arrows are the same length. Right? How long are they? Well, you just count it out. It looks like it's 10 seconds, right? 10 seconds here, or it's 10 seconds between these 2 points, or between these 2 points. All right, so t equals 10 seconds, which means omega equals 2 pi divided by 10 seconds, which is 0.628 radians per second. And I'll label that as well. Okay, so now I have everything I need to just put it into the equation. So I'm just writing down the equation. Alright, so the equation is x as a function of time is the amplitude, which is 2.5 centimeters, times cosine of omega, which is 0.628 radians per second, times t. And that is the mathematical description of this. Okay, the second question here says that we have an oscillator whose motion is described by this equation. All right, what is the maximum velocity and the maximum acceleration of the oscillator? So given what we just saw, we can read amplitude and omega directly from this equation, right? So the amplitude is 0.15 meters, and the angular frequency omega is 1.2 radians per second. Right, so how do we find maximum velocity and maximum acceleration? Well, if we recall, the equation for velocity as a function of time looks something like this. Minus a omega sine omega t. Right? So the coefficient, the variables sitting in front of the sine, those are the maximum velocity. It's the amplitude of the velocity curve, right? The velocity oscillations, really. So here, V max is a omega. All right, so while we're at it, the acceleration has an equation that looks like this. It's minus a omega squared times cosine omega t, right? So then a max is just the amplitude of that. It's a omega squared. Right, so using these two equations, I can calculate this. So we just take this velocity equation, and V max is simply 0.15 meters times 1.2 radians per second. And if you do that math, you end up with 0.18 meters per second. Right, we can do the same thing with the acceleration. A max is 0.15 meters times 1.2 radians per second, and that quantity is squared, and that is 0.216 meters per second squared.